Hello students, today we will do thermodynamics push theory part 1. So what are the topics that we are going to cover today? So starting from the fundamentals, we move on to the extensive and intensive properties, state and path function, types of processes, work, heat, internal energy which can be represented by E and U both. Then we have the first law of thermodynamics and then we have the enthalpy. So let us start our today's class. Disclaimer, the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@itk.ac.in and we shall remove the images. The first topic is fundamentals of thermodynamics. So, the laws of thermodynamics deals with the energy change of macroscopic systems involving a large number of molecules rather than a microscopic containing few molecules. Now, what is the meaning of this is that your thermodynamics law that we will now study we will study first law, second law, third law. All of this law are applicable to bulk, means a large means particle present in a small amount means massive particles basically. So we can't apply this laws to small particles such as electrons, protons, and neutrons. They are not applicable. Okay, so this is the fundamental thing. This is the thing is that you should remember regarding thermodynamics, and it's very important. So keeping this text in mind, we will move on to the fundamentals. First, we will see some terminology. So starting from system and surrounding. So what is system? The system is basically that part of the universe under which is under observation, and the part of the universe except system is called surrounding. Clear? So what are we doing saying here? We are saying here is that only that part of system is considered as your system where we are doing our reactions or where we are seeing the reaction. So the area under our observation is taken as a system. Now, except that part of the system, every other part is considered as your surrounding. So that thing is being mentioned here. System is basically a specific portion which is considered under the thermodynamic studies. Clear? Now, the system where the reaction is taking place or where our observation is done and the left part which is the surrounding, if you add both of them you will get your universe. So universe can be written as sum of system plus your surroundings. Clear? Okay, so this is the first terminology that is very important. You will often encounter this word system and surrounding. Clear? Now moving on further. So on the basis of mass and energy exchanges, system are again classified into two types. Miss, we will see that whether a given system is able to exchange mass, means whether it is change, whether the molecules are going in or out or not. That thing we will just see, and whether the energy that is being released by the system is going to the surrounding or not. That thing we will observe. So keeping these two exchangeable properties in mind, we will move on to the say types, right? So open system. So what is open system? Open system is one where the energy and mass both can be exchanged. So what is the meaning of this? So suppose you have a closed, sorry, no, you have not a closed system. You have a open tea cup. Okay, it is filled with tea. Now the tea has been, say, able to be evaporate. Or if you take a bucket of water, also that has an open lid, that water will also turn slowly into vapor. It will undergo evaporation, and the part of the water will be going to the surrounding. As a result of that, your mass that is present in the bucket will reduce, and the mass of water vapor will be transferred onto the surrounding. So there is a possibility of matter exchange. Second thing, if you take suppose you take the water in the bucket to be hot. Okay, you take the hot water. Now what will happen? Since the surrounding as compared to your hot water is cool, so this water will slowly release heat, and that heat will go into the surrounding. So this is a kind of what? Energy exchange. Clear? Okay, so these are the two types of phenomena, energy and matter exchange. And keeping these two in mind, we will define later system terminologies. Okay. Next is our closed system. So what is closed system? So in closed system, only energy. Okay, means only energy can be exchanged. So suppose you kept that lid closed. Okay, you put a lid on the water, hot water. Now what will happen? That slowly this container will radiate heat. Okay, it will radiate heat, and but the mass that is present inside will not be allowed to escape due to the lid closed. So in that case, we will call that system as closed system. And the last one is isolated system. So what is isolated system? In isolated system, we will take a thermos flask for example, so which keeps the water hot for longer time if you keep it hotter, and it keeps the water cold if you keep cold water for a longer time. So what happens in that case? So in that case, you are neither able be able you are neither be able to exchange energy nor the mass, because now it is being insulated using a thermos flask. Yes, but it is true that at 100% insulation is not possible, but to up to a very good extent, this thing works. Next property is based on the state of the system. So it is used to define the state of a system, and it are of two types. These are of two types: extensive property and intensive property. So properties are what? So it is define the state of system. Suppose your pressure, volume, temperature, internal energy. You will pressure, volume, and temperature. You must have heard of it earlier. Internal energy is a new term. It is in thermodynamics, enthalpy, and all of these terms are related to thermodynamics. They all are what? They all are properties. Sometimes they're also referred to as functions. So we can also get extensive and intensive functions. So we have no problem. We should have no problem with that. Now, what are intensive properties? So intensive properties are those which depend upon what? Which depends on the nature of matter. Means it means that suppose you have a say say you have a volume of gas. Okay, you have a volume of gas. Now what you do? You divide that volume into two parts. Now those two parts are divided such that the volume become half. Clear? Initially, suppose the whole gas has a temperature of T. Now each of the compartments that you have divided your whole system to, both of them will also have a temperature T. So in this case, what is being observed? That your temperature is not changing, although you are changing the amount of or mass of gas. So that thing is called what? Those are called extensive property. So also suppose the pressure will also not change in that case, temperature will also not change, and all the specific and molar properties will not change, because in specific and molar properties you already define the amount of substance. So change in amount of substance cannot affect this property. Clear? Next is melting point. Again, same thing. So if you are taking 1 kg of water or one sorry, 1 kg of water or 2 kgs of water, it would be more appropriate if I talk about volume. So suppose I take 1 liter of water or 2 liter of water, both will have the same melting point at a given pressure. Right? So that is very obvious. Next is extensive property. So the opposite of the intensive property is the extensive property. So it depends upon the quantity of the matter, like your internal energy, your heat, total moles, volume, enthalpy, entropy, free energy, it etc. So moles is obviously extensive property. You change the mass, you are changing the number of moles, because the formula itself involves a given mass. Clear? Next is volume. So volume is, you have seen that you take that gas partition example again. So if you are partitioning in two parts, two equal parts, then a volume is also getting half upon decreasing the mass. Similar thing is for enthalpy and entropy. So remember that these three are extensive property. We will see how it will be. And this free energy also. All the thermodynamic properties, like not all the thermodynamic properties, this functions like your internal energy, enthalpy, or say your Gibbs free energy, entropy, Helmholtz free energy. All of this will be what? They all will be your extensive property. Now force is also an extensive property, but pressure is an intensive property. Now what is the meaning of this? So what is the formula of pressure? First of all, pressure is given by force by area. Okay, force per unit area. So force is an extensive property and area is also an extensive property, right? So both are extensive property. But but the division of both of this is what? An intensive property. Clear? Which is a pressure. So we can make a general statement that the division of any two extensive property will always be a intensive property. How can we see it? So I've already said you that specific heat is a what? Intensive property. How can we say that? So what will be the formula of specific heat? So it will be heat by 1 gram of a substance. That will be a specific heat. Now 1 gram, it is mass. So mass is extensive property, obvious, very obvious. And your heat is also extensive property. We have seen this. Now both of this is extensive. If you divide both of them, you will get an intensive property. Clear? Now moving on further. Next are state function and path function. So first is state function. So state functions are those whose values depend upon the initial and uh, final state. Initial or final? You can say state very well. Okay. So it depends on the initial and final state only. It does not depend how that state is reached. Suppose you are moving from state initial to a final state 2, which is the final state. So in transitioning from state 1 to state 2, you can do it in various ways. Okay, suppose you are having an intermediate state, that is S3, or there can be a way that you are directly going from S1 to S2. Now in both these cases, your values of state function will remain same. So those will be pressure, volume, temperature, delta H and delta U. Now what is the use of this? The use of this is that you can easily calculate the change in the function by knowing the first and last value, and you will just take a subtraction of that, that is final minus initial, and then you will be able to see that the volume of these are not changed. Clear? Means that change is remaining constant, as well as their values are also remaining constant. So you are going, suppose, from T1 to T3 to T4 to T1. Now your final temperature will be T1. You don't have to worry that how the temperature is reached. Same it goes for volume and same goes for temperature. Next is path function. So for path function, what we will say? That for path function, the value will depend on the path that has been followed. So whether we have taken a third step or not, whether we have done it reversibly or irreversibly, that thing is also mentioned. So all of the things are mentioned. So if it is say depending upon path, the value of function depends upon path, then it is called as path function. So work done and heat are the examples of it. Clear? We are moving further on the types of processes. So the state of a variable can be changed by means of thermodynamics process. So there are various types of processes. So since the path functions are dependent upon path, so if you take the processes in various means if you do the work through various processes, you will get different values for that. Now the process can be of various types, starting from adiabatic process. So if you do a work adiabatically, means you are keeping the heat change constant, because you are not heat change constant, you are keeping the heat supply zero. Yes, so that thing is called adiabatic. So Q will be equals to 0, or dq amount of heat is not transferred. So both are true. Means there is no change in the amount of no amount of heat is being transferred in this case for the adiabatic process. Then we have isothermal. So in case of isothermal, we see the change, right? So the change of temperature is what? 0. In case of adiabatic, we see the exact value, means no amount of heat should be transferred. But in case of isothermal, it is not possible to keep that no temperature will be there. So what we say that your temperature change should be 0. Clear? Similarly, isobaric process, the change of pressure should be 0. So this process called is done at constant pressure. And at last we have the isochoric process, in which your change of volume is 0. Right? In this case, your change of volume is 0, means you are not changing the volume. You are doing your process by keeping your volume constant. And then we have the cyclic process. So in this cyclic process, what will happen? You will start from the suppose state 1, you will move out into state 2 or 3 or 4, but you will return back to the same state 1. Means the initial and final state of the system are same. Now when we are saying state, what are we meaning by this? What we mean by this? We mean by this that your all the values of state function will remain same. So this is the meaning of this. Suppose you are starting from pressure P1, V1, T1, internal energy U1, H1. H1 is the enthalpy. Now, when you end your cyclic process, then the value of your pressure, volume, temperature will be same. That is P1, V1, T1, internal energy E1 and U1 enthalpy. So all of this will have the same values. There will be no change in that. So those type of processes are called cyclic processes. Next is reversible process. So this is very 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 important for you. So what are reversible process? So reversible processes are those in which we change the system by introducing infinitesimal changes. Okay, so we introduce very small amount of change to move from one state to another. So this thing is kept in mind. So why this is done? Because in this type of processes, the reaction can be reversed at any point, because we are doing or we are changing it by introducing small changes, right? So every intermediate state in equilibrium with each other, if any. So the reversible state is an ideal process, and here every intermediate state is an equilibrium with each other. So you move from one state to another by introducing small changes. Suppose you have increased the pressure by a small amount, that is dp. So that will be in equilibrium with the first state. Then we move to we'll add one more dp and then one more dp, and doing this slowly and slowly we'll move to the where final state. Clear? Okay. Next is irreversible process. So in irreversible process, what is being reminded? That your process cannot be reversed. Means you process once you start, the process cannot be reversed. And in this process, the value of say change is not small, as was in the case of reversible process. One very important point, that the natural process that you all see are irreversible. So this should be in your mind, that whether the falling of water from a height or ripening of your fruit, or you say flowing of a river, all of these processes that you see around you are irreversible. They cannot be reversed. Clear? Now, if your microscopic properties like temperature, pressure, etc. do not change with time, then the system is said to be in equilibrium. And if two systems are in thermal equilibrium, the third system, then all three are in equilibrium with each other. So this is called as Zeroth law of thermodynamics. So suppose A and B are in equilibrium with each other, and at the same time A is in equilibrium with C and B is in equilibrium with C, then A, B and C will all be in equilibrium. Or we can say in a much pronounced way, that suppose your A is in equilibrium with C and B is in equilibrium with C. That means A and B are also equilibrium with each other. Clear? Now this law defines the property as defines the temperature as the property whether the body is in thermal equilibrium or not. Okay, these laws define. Now moving further. Further we will see what is work. Okay, we will see what is work. Okay, so moving on to work. So work is said to be done when gas expands or contracts against the external pressure. So when what we do, we suppose we are applying a greater pressure from outside, and the piston that is being implied to uh, do the work of lid is frictionless. Then your friction will move inward and decrease the volume, and the reverse of that is also true while expanding the gas. Now work done is a path function and not a state function. It should be remembered, and depends upon the path that is followed. So this is very very important, that a work done is a path function and not a state function. Its formula is work done is equals to minus P external delta V, and your V2 is greater than V1 if you are writing it as V2 minus V1. Now for compression, the formula is same, but the thing I want to make you see is that for expansion, what is the system is doing the work, therefore your work done will be negative. But for compression, your system the work is done on the system, so it will be positive. So this was the irreversible process. So for reversible process, what is the formula? It is minus 2.303 nRT log V2 by V1. Now this is also true for this formula is also true for reversible, but instead of delta V, we will write it small change, that is dV. Then what we will do, we'll substitute P external with nRT by V and we get this equation. So this equation is derived from this equation only. So you don't have to worry about it. So it is already mentioned V2 is the final volume, V1 is the initial volume. W reversible is given by minus 2.303 nRT log P1 by P2. Next is that the maximum work done in isothermal reversible expansion. First is intermediate expansion. So this is written that your maximum work done for irreversible isothermal expansion. So what is intermediate expansion? So in intermediate expansion, your P gas is greater than P external, and the formula will be W irreversible is integration of V1 to V2 for P external dV. Or since it is irreversible, you don't have to integrate, and you will get minus P external V2 minus V1. Now in case of free expansion, what it has been seen that P external is 0. So what is free expansion? Suppose you are compressing the gas with a high pressure. Now you suddenly remove the lead, then compared to the atmospheric pressure, the inside pressure is very large. So it will expand quickly and look like a free expansion. So since for free expansion, the external pressure is 0, therefore your work done will be 0. Clear? Next is sign convention. So if work is done by the on the system, it is positive. If it's done by the system, it is negative. Clear? After that, we have heat. So what is heat? So it is basically a form of energy only. So we are supplying energy from outside to inside the system. So that is being defined as your heat. Now it is also a sparse function because it again depends upon the part that has been taken. So our sign convention, if heat is supplied, then it is positive. If heat is lost, then it is negative. Then we have internal energy. So this is very, very important. What is internal energy? So internal energy is basically the sum of all types of energy a molecule possesses, including translational energy, vibration energy, potential energy, etc. So every energy that a molecule possesses is called a what? It's called the internal energy. Sum of all of this is called a internal energy, and we can only determine the change in internal energy because it is very difficult to analyze each and every type of forces that is present inside the molecule. So we only focus on the change, and that is our important part also in a way. So we are say looking for the change, so u2 u minus u1 can be written as change. Clear? Now, as the pressure is temperature is constant, internal energy change will be 0. So you will see that how it will be 0, and internal energy depends upon temperature, pressure, volume, and quantity of matter. So you can see it very clearly that it depends on quantity of matter, so it will be extensive property. Okay. So we have seen internal energy, we have seen work, we have seen heat. Now let us see first law of thermodynamics. So that will make the sense. So according to this law, energy can neither be destroyed nor be created. It is always converted from one to another. So if you write the mathematical form of thermodynamics, then it is written as delta U equal to Q plus W. It means that every heat you supplied and every work you do, all of this are adding to the internal energy change. Clear? No heat is lost by a system. So both W and Q are not state function, but W plus Q is a state function. Okay, this is very, very unique to see that you know that Q and W are what? They are path function, but the addition of both of this is a state function. So you don't have to derive at a general conclusion. I am just saying it. But that property, that extensive by extensive property will give you intensive. That thing is very, very important. Clear? After that, we have enthalpy. So enthalpy is nothing but the sum of internal energy and the product of pressure volume work. Okay. So if you take the sum of this and this, then it will give you the internal energy. So again, it is a state function, extensive property and a state function, and it is represented by H. So if you write this thing, that is delta H equal delta U plus delta PV, then if you keep the pressure constant, right? If you keep the pressure constant, then P will come out and delta H U is equals to delta U plus P delta V. And if you don't replace this, don't keep the pressure constant, then you can replace this PV by nRT, and RRT are constant, so therefore delta NG RT will be a formula. Yes, so this equation is also very important. This will be used in reactions multiple times because in this case you're keeping temperature constant and instead you are getting your enthalpy. And the reason is that you're doing a chemical reaction. Ng is what? So we are applying gas law here, na? So this is the change in number of gaseous molecules from product minus reactant. Now if Ng is 0, then it's delta H is equals to delta U, very obvious. If it is not 0, if it is greater than 0, that means delta H is greater than U. And if it is less than 0, then delta H is less than U. Okay, so this is the thing I want to make sure you remember. So for a reaction involving solid and gases, solids and liquids, only delta H is equals to delta U because no gas is released. If no gas is released, then what is the meaning of this? That your change in number of moles of gases will be same and your delta H will be equals to delta U. So let us try to sum up with a summary. So first of all, universe is nothing but a combination of system and surrounding. And if you talk about the fundamentals, so we have open system in which both matter energy can be exchanged, closed system energy can be exchanged, and isolated system nothing can be exchanged. Extensive property which depends upon the amount of property, which intensive property which does not depend on the amount of property, and extensive which depends upon the amount of property. Now one more point I had not made it there, so I will make it here. That if you know the value for 1 gram of a 1 mole, then you can calculate it for multiple gram or multiple moles respectively in case of extensive property. But in intensive property, you can't do so. You can't add intensive or extensive property. You can add extensive property, but you can't add intensive properties. Clear? Now next is state function. So it depends upon the initial and final state. So those functions are called state function. And path functions are those which depends upon the path that has been acquired to reach the final state. If we talk about the types of processes, so adiabatic process, heat is not supplied. Isothermal, change in temperature 0. Pressure, change in pressure 0. Isochoric, change in volume 0. And uncyclic, where the initial and final state are same. Next is reversible process. So a process which is always in a quasi-static system, means from any point it can be reversed to the initial point because we are introducing small changes to do the overall reaction. In irreversible process, we do the whole reaction in one go and it is not reversible. So in this case, reversible case, your formula is minus 2.303 nRT log beta V1 or minus 2.303 nRT log P1 by P2. Now, if work done is to be calculated, it is minus external P minus P external delta V. And for what is first law of thermodynamics, it says that matter cannot be destroyed, not be created. So every heat is supplied and every work you do goes on to addition to your change in internal energy. So this formula I told you that if you keep the pressure constant, you will get this formula. If you're not keeping the pressure constant and your reaction involves gaseous molecule, then you get this formula. Or either you can use this formula also. Now this was all for today's theory session. Thank you.